Okay, so for this example, we will be looking into our problem of searching. So let's say we have a sorted list of student numbers enrolled in EEE 121. For example, let's have only 10 student numbers to simplify our discussion. So, for example, we want to know the index of a particular student in the list. So, for example, student number 6769, uh, we should call a function index of that searches the index of 6769, which is 4. So, if we try to search for a student number not on the list, the function should return -1. So the straightforward and lame approach is we can start checking the elements in our list one by one, starting from the first digit, starting from the first index. So starting at I equals 0, we check each element in the list. So starting at index 1, we check it. If it's equal to the key, we return what I is. Otherwise, we look at the next digit and so on and so forth. So now since here we called index of 9932, we will be checking each digit until we reach our key. Okay, that took a while. So that's why it's sort of a lame approach since we sort of needed to we sort of had to wait for it to finish, right? So let me just so here our worst case time complexity for the linear search is of n. So that's why it's actually called linear search. So depending on how many elements we have on the list, the worst case is we have to check each and every one of them. So this implementation has a big O of n. Now for the space complexity, we only really used an extra counter here. So we don't really have much complex space complexity to talk about. So it's just a constant. So in the next video, I will be revealing our CHAD binary search approach.